Jai Hind students, in today's lecture we will understand conflict serializability. So we will understand the concept of schedule equivalence so that we can understand the conflict serializability and the view serializability. So in this lecture we will cover only conflict serializability concept. So if we talk about the serializability, first of all we need to understand the schedule equivalence, right? So what do you mean by schedule equivalence? So first of all we will understand what is the schedule basically. So schedule is nothing but if 2 or 3 transactions are there in a schedule, then we can say it is a if we are having 2 transactions, right? So if we are combining these two transactions in a one schedule, then we will say it is a schedule, right? If we have a combination of 3 transactions, then we can say that it is a schedule, right? So when we will say those schedules are equivalent, so we will say the schedules are equivalent when it consists of the same transactions and if they produce the same result. So when we will say schedule equivalence, when 2 schedules consisting of the same transactions produces the same result, then we will say schedule equivalence, right? So schedule is nothing but the combination of some transactions, and we can say those schedules are equivalent when there are number of transactions same and they are producing the same result, right? So 2 forms of schedule equivalence are there. One is the conflict equivalence, another one is the view equivalence, right? This conflict or view equivalence leads to the notion of conflict serializability and view serializability respectively, right? So in this lecture we'll focus on this conflict serializability. Okay, so conflict equivalent, or we can say the conflict serializability, we can have this situation if I1 and I2 are consecutive operations. Here we are considering I1 and I2 are consecutive operations of 2 transactions of a schedule S, right? And these operations are such that I1 and I2 are non-conflicting operations. Okay, so if I1 and I2 are non-conflict operations in a schedule, and if we swap the order of I1 and I2, we expect the new schedule as just, right? And S does produce the same result as produces by S. So the order of non-conflicting operations does not matter. So we can create multiple schedules or multiple equivalent schedule, which also known as conflict equivalent schedule, or we can say the conflict serializable schedule, if we are swapping non-conflicting operations. What about when we swap conflicting operation? Then we cannot be able to produce the serial schedule. So when one will be able to produce the conflict equivalent schedule or conflict serializable schedule when we are swapping the order of non-conflicting operations. So I think this must be clear to all the students. Okay, now we can consider one of the example. If we consider a schedule S, this is the schedule S. This schedule S considering having 2 transactions T1 and T2, where are some operations on different databases, right? So if we generate a schedule S1, this one, by swapping the order of non-conflicting operation. First of all, we need to understand in this schedule what are the operations which can be considered as non-conflicting operations. So conflicting operations are basically if there are read and write operation, if there are write and read operation, if there are write and write operation, then these three operations are considered as conflicting operations. If there is an operation read and read on the same database, so this is known as non-conflicting operations. So conflicting operations are these. Okay, fine. So just a minute. Okay, so here if we consider these two operations, these are non-conflicting operations. If we consider this and this operation, it is conflicting operation, because one is the write on A and one is the read on A. So read, write, read conflict is there. Okay, if we consider these two operations on different transactions, it is a write conflict. If we are considering these two, there is no conflict, because write is happen on some data item and read is happen on some other data item. So there is no conflict. If we consider these two operations, there is a conflict, because one is the write operation, one is the read operation, and both are on the same data item. If we consider these two, these are conflicting operations. So now we have understood what operations are conflicting operations and what other operations are non-conflicting operations, right? So now we need to make a equivalent schedule by swapping the non-conflicting operation. So what are the non-conflicting operations? If we consider these two operations, these are what? Non-conflicting operations. So we can swap the order of these. Why these are non-conflicting? Once again, we can have a look on that, because these two operations are performed on different data items. That's why these are non-conflicting operations, right? So we can swap the order of these. Okay, so here we can see the equivalent schedule in which we have swapped the order of this. We have swapped the order of these two operations. So this is what the conflict equivalent schedule of this S, right? So by this way we can create multiple schedules which are non-conflicting schedules. We can have a look on these non-conflicting operations. After schedule S1, we can make the schedule S2, S3, S4. These are concurrent and conflict equivalent schedule, right? Here we can see this S5, it is serial schedule, because interleaved operations are not there. Once this schedule is executing, transaction T1 will be executed. After that, transaction T2 will be executed. So this is what transactions are executing in a serial order. But here we can see operations are interleaved, here, here and here. In these three transactions are what? Concurrent transactions. So after the schedule S, we can have the multiple conflict equivalent schedule of that schedule, S1, S2, S3, S4, and one is the serial schedule S5. Okay, so these schedules are conflict equivalent schedule to the serial schedule S5 also, right? Okay, so now we are able to define with that example, if a schedule S can be transformed into a serial schedule S dash by a series of swaps on the non-conflicting instructions, we say that S and S dash are conflict equivalent, right? So now you must understand the concept of conflict equivalent schedules, right? So if we are able to make a serial schedule from a concurrent schedule by swapping the number of operations, we can say that the obtained schedule is the conflict equivalent to the other schedule. Okay, the schedule is, if we consider this schedule as, it is a conflict serializable schedule if it is conflict equivalent to the serial schedule. So now we are able to define it. What do you mean by conflict equivalence? What do you mean by serial schedule? What do you mean by conflict serializability? Or what do you mean by a schedule is known as conflict serializable schedule? So these are the definitions. We have established this definition with the help of that particular example, right? So then schedule S is the conflict serializable as it is the conflict equivalence to the S5 schedule, right? So we have started with the S. In previous slide we can say see that we have started with the S, we have created this S1, after that we have created S2, S3, S4, at last we have created this serial schedule S5. We have started from S and we have created this schedule S5. So now we are able to conclude that S is the conflict serializable as it is the conflict equivalent to the S5, right? So these are the definition we have established. Okay. Now we need to test a particular given schedule is a conflict serializable schedule or not. So to test this, we need to make a graph, right? So this graph is very easy graph and it is known as the precedence graph or serializability graph. This graph can be made on the basis of read and write operations in the schedule. Other operation we will ignore. So we will consider only read and write operation in the schedule. Okay. So how we will make this precedence graph? This precedence graph is nothing but the directed graph in which N are the number of nodes and E are the directed edges. So N is the set of number of nodes and E is the set of directed edges. Now, how many nodes will be there in a precedence graph? For each transaction Ti in a schedule, there exists a node in the precedence graph. So if a schedule is having 3 transactions T1, T2 and T3, it means what? That graph will have 3 nodes, right? If a particular schedule is having 4 transactions named T1, T2 and T3, T4, it means what? The precedence graph of that schedule will have 4 nodes. Now come on the edges. An edge EI in the graph is shown as how? Ti edge will draw the edge to Tj. It means Ti is the starting node and Tj is the ending node for the edge EI. Okay. So edge are created in the precedence graph when the conflicting operations exist. So when we will create an edge? When we have some conflict operation, right? Okay. So this is the algorithm basically to construct the precedence graph. We have understood how many edges will be there, how many nodes will be there, and when we will create an edge. We have understood that. Now the set of steps to create the precedence graph. Okay. For each transaction Ti participating in the schedule, we will create a node labeled Ti. Very fine. If Tj executes the read operation after Ti executes the write operation on any data item, let's say A, will create the edge Ti to Tj in the precedence graph because it is a conflicting operation and we will create an edge for each and every conflicting operation in the precedence graph, right? Now, I have told you how many conflicting operations are there. Read and write, write and read, and write and write. So we can see here these 3. 1, read operation after write. So this one. Ti executes write operation after Ti executes the read operation. This case. So we'll create this edge. Third one, Tj executes a write operation after Ti executes the write operation. This case. So there is a conflict. So there are these 3 cases, where we need to draw an edge. As a resultant, precedence graph is acyclic, then the schedule S is considered to be the conflict serializable. If cycle exists, schedule is not conflict serializable. So this is the test for conflict serializability, right? So there are basically 4 steps. One, to create the nodes, and these 3 steps to create the edges, as 3 conflicting situations are there. And fourth one, to judge. Fourth one is to judge that that particular given schedule is conflict serializable and or not. So if there is a cycle, it means what? That is not conflict serializable. If there is no cycle, it means what? The schedule is conflict serializable. Nice. Okay. Now the other concept we need to have to make a equivalent serial schedule, right? So if an edge Ti to Tj in the precedence graph implies that the transaction Ti must appear before Tj. If we have an edge Ti to Tj, it means what? Ti appears before then Tj in the serial schedule. So by this way we can make the serial order, right? So if there is no cycle in the precedence graph, what we will see, the schedule is conflict serializable and we are able to produce the serial schedule. Okay, so we need to produce a serial schedule, right? How we will decide the order? We'll decide the order by this ordering. Okay, so if there is this H exists, it means what? Ti will appear first and after that Tj will appear, right? So this will be the ordering of the transaction in a particular schedule. Okay, we'll have the example so we can understand more. So at last we can say this ordering by which we are calculating which transaction is coming first, which transaction is coming after that. It is known as the topological sorting. So the the process of ordering the node of an acyclic precedence graph is known as topological sorting, right? So it produces the equivalent serial schedule. Okay, now we will have a very small example with 2 transactions in a schedule. So this is a schedule S in which there are some transactions, some operations. So before also I have told you that we'll consider only read and write operations, not other operation. All other operations are ignored. Okay, so we need to check this particular schedule is conflict serializable or not. So if schedule is given like this, we need to make a figure in tabular form first. Okay, so as we have seen here, this is schedule S in which there are 2 transactions, because we can see here R1, R2, R1, R2, W1, W2. It means what? 2 transactions are there. Some read and write operations are from the transaction T1 and some of read and write operations are from transaction T2. Okay, so here we are making T1 and T2. R1A is coming first, so we'll write first this. R2A coming after that, so in the next line we will write this. R1B is coming after this, so we'll write in the next line. R2B coming after this, we'll write in the next line. W1A is coming after that, we'll write in the next line. W2B coming after that, we'll write in the next line. Okay, so by this we can make this table. Now we will check for each and every schedule. So we'll start from first operation. We'll check there is a conflict is there. No conflict is there because both are the read operation on same data item. So no edge will be drawn here. We'll check the next R1 to this because both are the read operation. Moreover, both are read operation on different data items. So no point of drawing an edge. R1, W2, conflict is there, but because R1 is going on, reading is on data item A, writing is on data item B. So there is no conflict. Okay. So we have checked this with each and every operations of the other schedule. Now we'll check this. Okay. So we'll check this with this R2, no conflict. This one, yes, there is a conflict, so we'll draw an edge from here to here and make a direction here. Okay, and then we will consider this. So no conflict, yes, there is a conflict, no conflict, no conflict. So only two edges will be drawn. So in this figure, what we have drawn, because a schedule is having two transactions, so we have created two nodes, T1 and T2, right? And here we have checked that one edge will be from T1 to T2 and another edge will be from T2 to T1. So what we have drawn these two edges. Now what we can see, there is a cycle. Okay, so there is a cycle in the precedence graph, hence the schedule is not conflict serializable. So this is the checking. If there is a cycle, schedule is not conflict serializable. Now we can have another example. Okay, so in this example we have taken some more complicated example. We have taken a schedule in which there are 4 transactions, right? So how we will make that precedence graph? How many nodes will have this precedence graph? T1, T2, T3 and T4. 4 nodes will be there because there are 4 transactions in a schedule. Okay, so we'll see that transaction T2 is having the read operation first. So we'll check this Rx with this. There is a conflict because read write conflict on same data items. We'll draw an edge like this. Okay, now we'll check this with the next operation. Yes, there is a conflict, read write conflict on same data item. Okay, so we'll check with this, no conflict, has read on same data item, read on different data items, no conflict. This is done. We'll check the next operation. So next operation is what? T3's write X. We'll check this write conflict on same data item. So we'll draw an edge. Okay. So as we are drawing these edges, we'll write the ordering of edges here. So first of all, what we have written, just a minute. R2 X to W3 X. First edge we have drawn, and the second edge is R2 X to W1 X, and the third edge is W3 X to W1 X. Okay, so 3 edges we have drawn, and the next we'll check this no conflict, no conflict. Yes, there is a conflict because write and read on same data item. Here no conflict. So the next is W3X to W4, not W4, I4, read. So this is the next edge we will draw. Okay, so now we need to check this. The next operation is this, no conflict, no conflict. Yes, there is a conflict. So this is what the W1 X to R4 X. Next we'll check with this, no conflict. but here we can have the conflict. So we'll write this R4 Y. Okay, so this is what R4 Y. So any other edge is remaining? I think no edge is remaining, all we have done. So we'll check, is there any edge R2 to W3? So T2 to T3 there is an edge, T2 to T1 there is an edge, T3 to T1 there is an edge. Now T3 to T4 there is an edge, T1 to T4 there is an edge, T2 to T4 there is an edge. So this we have drawn. Now we'll check there is a cycle or not. So if there is a cycle, means the schedule is non-conflict serializable. So we can see that there is no cycle. So if no cycle is there, it means it is conflict serializable, as well as we can make a serial schedule also. So this is, we can conclude that this is conflict serializable schedule. So we have reduced this. Now we need to make the ordering in which the serial schedule will appear to us, right? So we can see that T2 is coming first. So I need to write here T2 is coming first, then T3, then T1. So what is remaining? T4. So this is what the ordering of the transactions which will appear in case we make the serial schedule. So what we have reduced is here, what we have checked here, the given schedule is conflict serializable and we can make the serial schedule in this order. So both of the things we have reduced here. Okay. To understand better, we may have one more example. Let's suppose we have given a schedule this with some of the transactions. How many transactions are there? 3 transactions. So first step, what we will do, we'll make a table T1, T2 and T3, right? So I'll make a table for that. Okay. Now first operation is appearing, read operation. So we'll write read X here. Just a minute, we need to write clearly so that you need to understand properly. Okay, so this is nothing but R1X. Now the next operation is coming after this, so we'll write in the next line R2Y. Now the next operation R3 Y. Okay, the next operation W2Y. Next is W1X. Next is W3X. So I'll write in the next line R2X. I'll write in the next line W2X. This is overwritten again and again. So this is nothing but W2X. So we have made this table. Okay. Now we need to find out where we need to draw edges. So first of all, as there are 3 transactions, we'll write T1, T2 and T3. Now notes are here, but now we need to draw edges. So we'll start from here, from R1. So there is an edge between this? No, because both are read and on different items. Here there is an edge, here there is an edge. No, because both are on operations are on different data items. So we'll check, here is an edge. No, because both are reading. Here is an edge, because read and write conflict on same data item. Here is an edge, because read and write conflict on same data item. So 2 edges we have drawn. We'll check this. No, no, on different data items. No. And the next operation, this, yes, there is a conflict. So we'll draw an edge. This, there is no conflict on different data items, on different. So till now we have reduced that we need to make 3 edges. First is R1 X2 W3 X. Second one is R1 X2 W2 X. Third one R3 Y2 W2 Y. 3 edges we have find out till now, which will be drawn in this. Okay, so here we have edge, here no edge, no edge, no edge. So the next operation will check W2Y. No edge will be drawn. The next operation, this W3X, will check R2W. Yes, there is a conflict, but as we have drawn this edge T3 to T2 already, so we'll not draw an edge, because once we have drawn that edge like T1 to T3, okay, and this T1 to T2, okay, T3 to T2, right. So we have drawn these edges. Now we have find out that T3 to T2 there is an edge, but we have already drawn an edge from T3 to T2. So no need to write again and again. Okay. So there is an edge from this. So we have drawn this. Okay. So only 3 edges will be there in the graph. Now, as we have not able to see a cycle in this graph, so this is what the conflict equivalent or conflict serializable schedule. Now how we will make this serial schedule, in which order these transactions will appear. So these transactions will appear T1, then T3, last what is remaining, that is T2. So this is the ordering or topological sorting of the transaction when we will make the serial schedule, right. So we have understood 2 concepts here. One is conflict serializability. We have find it out how we can make the conflict serializable schedule, or we are just find it out how to test the given schedule is conflict serializable and not. Or and another thing we have drawn as the ordering of the transaction when we will make the serial schedule, right. So this is how we will reduce. We can have more examples on these. I will give you more examples so that you can have the practice on that, right. So thank you so much. In the next lecture we will continue with the view serializability and the test for the view serializability. Thank you so much.